and you thought we were all done with winter. Well, welcome to part 4. Number 37. Simplify the expression. Assume that variables represent non-zero numbers. Okay, simplify means, well, obviously it's real complicated the way it is. We're going to get to the answer. The other thing is assume the variables represent non-zero numbers. If s that's in the denominator was 0, then it would be undefined. If there was a 0, p or v were 0, then the whole thing would be 0. So they want us to assume that that's not the case, so we have to solve it, right? Okay, so 3p to the second power, v to the third power, over s to the second power, all of that to the third power. Now we can look and we see there's nothing to cancel out inside the parentheses. So it means that everything there is to the third power. The whole thing, this whole thing, is the base. So let's solve it. This, if you remember the rule, everything inside there, everything inside the base, is to the third power. It's going to be taken to the third power. So this becomes 3 to the third power. Everything in there, everything, not just the variables. P to the third power. We've got p to the second power. That's to the third power. We've got v to the third power, and that is to the third power. And then s to the second power is to the third power. See, this is one way to do it. This is not the way I'd usually do it, but this is one way to do it. So 3 to the third power, that's 27. P to the second power to the third power, so there's 2 p's, and that's 3 times. So that would be p to the sixth power. V to the third power to the third power, v to the 3 times v to the 3 times v to the third power, that's 9 of them. V to the ninth power. And that's over s to the second power. So s to the second times s to the second times x to the second is 6 of them. S to the sixth power. And that's it. It's solved. We can do it another way, though. We could say, all right, this 3p to the second power, v to the third power over s to the second power is to the third power. So there's 3 of them. Okay, so if we can't figure it out from here, if it's still confusing, we could break it down even more. Maybe we just take one of them and break it down even further to what it is. See, so we've got 3, 2 p's, 3 v's, and that's over 2 s's. Okay, and that whole thing is 3 times. There's 3 of them. So 3 times 3 times 3 is 27. And I could put those in there if I wanted to. I could do this, and it doesn't actually, see, it doesn't take that long to break it all down. I could just add them up. So 3 times 3 times 3 is 27. 1, 2, 3, 4, 5, 6 p's. P to the sixth. 1, 2, 3, 4, 5, 6, 7, 8, 9 v's. V to the 9. And it's over how many s's? 1, 2, 3, 4, 5, 6. S to the sixth. So what looks like a very complicated problem is actually quite an easy problem if you break it down. And it didn't take that long, right? Number 38, simplify the expression. Write the result using positive exponents only, as I said before. Okay, so this is equal to p to the fifth times what? Well, this p to the negative 9, we'll bring that on the top of the fraction bar, which leaves 1 underneath, and of course 1 into that number, we don't even need it underneath, right? So we'll just change this to p to the positive 9th. But for those of you that doesn't make sense to, let me do it this way. P to the negative 9th. Okay, so this becomes, that equals 1 over, no, it doesn't equal 1 over, it equals p to the 9th over 1. That's the reciprocal of that, only with the, it's got a positive power now, see? And that is times p to the 5th. So what we have here is we've got p to the 9th times p to the 5th, or p to the 5th times p to the 9th. Now if you get confused about what to do now, you see we have this p here is times itself 9 times. 2. Okay, there's 9 of them. And then the p to the 5th, that's times p to the 5th. 1, 2, 3, 4, 5. Okay, count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 equals p to the 14th power. Or, as you can see up here, p to the 5th times p to the 9th equals p to the 14th. You can just add the exponents. Okay, now here we have a standard notation problem, or a scientific notation problem. Standard form is what we're used to. Scientific notation is a shortcut to deal with really big numbers. And so we can display them, get a better idea of how big they are or how small they are, and also so we can multiply and divide them and do other processes to them. You could take square roots of them or whatever. So we were already used to exponents. We've had exponents. So the standard scientific notation deals with tens. For instance, 10 to the 1 power equals 10. 10 to the 2nd power equals 10 times 10 is 100. 10 to the 3rd power equals 1,000. Notice the 3 zeros, the 2 zeros, the 1 0. If we went the other direction, and as we keep going up, like 10 to the 6th equals a 1 with 6 zeros. 1, 2, 3, 4, 5, 6. It's a million. 10 to the 6th. 6 zeros. Okay, so what if we went 10 to the negative 1? Well, we know what that means is 1 over 10 to the 1 power, or just 1 over 10, right? Also, we could write it as a decimal. It would be 0.1. 10 to the negative 2 power would equal 1 over 100. 1 over 10 times 10, right? And that as a decimal would be 0.01. 10 to the negative 3 equals 1 over 1,000, or 0.001. Okay, so now notice here that this is the negative 1 as 1 0, negative 2, 2 zeros. As far as decimals go, the negative 1 has one with one decimal at one decimal place. 2 decimal places, a 1 with 2 decimal places, a 1 that has 3 decimal places. So 10 to the negative 16th power would be 0.0000000. It would have 15 zeros and a 1 on it. I'm not going to draw them all. Okay, so what this has to do with scientific notation is we use the fact that we can go 10 to different powers, positive or negative, and then we can use that to express numbers. So let's say we had this number, 5800000000, whatever that is, okay? 5,800,000,000. Okay, so you have 5,800,000,000 might not even fit in your calculator to work a problem. So instead, what we're going to do is we're going to take away some of these zeros and then instead multiply them times 10 to some power. Okay, to replace the decimal places that I took away. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So we'll change this to 5.8 times 10 to the 9th. Oops, where's my 10, right? Times 10 to the 9th power. Okay, so now what if we have a really tiny number? We can do the same thing with the really tiny number, only we'll be going in the other direction. We're going to make the number seem larger. You notice here we took a very big number and made it look smaller, but we made up the difference with all these tens. There's 10 to the 9th power, a 1 with 9 zeros, right? Okay, so if we had 0.000000000043. Okay, so that's a pretty tiny number. Let's do the same thing with that, only we're going to make it look bigger, right? We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's 11. So it would be 4.3 times 10 to the what? Negative 11th. See, because we made that number bigger, we've actually multiplied it by 11 tens. So we reflect that with this, negative 11. So 4.3 times 10 to the negative 11th power. So now we could divide those two numbers. We could divide 5.8 times 10 to the 9th power by 4.3 times 10 to the negative 11th power, because we know how to divide with exponents, and we also know how to divide and multiply with integers and other rational numbers. Okay, so let's look at this problem. Has us going in the other direction. Here we're going to put it back in standard form. So we've got 2.315, and it's times 10 to the 5th power. So let's put 5 decimal places back in. 1, 2, 3, 4, 5. That's like multiplying it by 5 tens. Okay, so this number in standard notation is 231,500. I think we'll get one of the other type in a second here. Okay, so we're going to convert this one to scientific notation, but then we'll convert it back, just so you can see going in the other direction. I'm going to just rewrite it because this thing I'm using is so fat. 0.000257. Okay, so I'm going to put in scientific notation. 1, 2, 3, 4. Decimal point's going to go there. So it's going to be 2.57 times 10 to the negative 4th power. Because I multiplied it basically by 4 tens, I've got to take them away now by using the negative 4. Okay, so let's say we were going to change this back into that. How do we do it? Okay, so it's to the negative 4 power, 2.57. Let's take those zeros back away. We'll go 1, 2, 3, 4. Decimal point goes here. 0, 0, 0. And you notice we're back to exactly the same number we started out with. One thing I didn't discuss was these numbers. Where does the decimal point go? So let's say I have 9872051, and I want to put that in scientific notation. Well, that's not going to help a heck of a lot because it's got so many digits in it. Here's where we would put, we start with it at the decimal point of this number, and we go in, we always start with the decimal point. So here we're going to go this way. 1, 2, 3, 4, 5, 6. So you see where I put the decimal point? After the 9. 9.87205 times 10 to the 6th power. Okay, I made a large number look small. And notice that I have just one digit here. One digit. It's always just one digit, and then after the decimal point there could be a lot of digits. Or usually there's one or two after the decimal point, or none. But on this side of the decimal point there's always just one. 9 is the biggest one it can be. It's got to be, the number that goes here, it's got to be less than 10. It's got to be less than 10, and it's got to be 1 or greater. So, I mean, if I could write that like if sometimes they're negative, so let's say that this number is B. No, let's not use B. Let's use S. I don't know why. Don't ask me why. Okay, so S has got to be greater than or equal to 1 and less than 10. So it's always got to have just one digit. You know, it could be 5.6, for instance, or 1.09. It's got to always have one digit, so it's got to be somewhere less than 10. It's got to be, if it's 9.99999, we would go 9.99999, you know, but it wouldn't be 10, right? And there's only one digit here. So that tells you where to put the decimal point. You can always leave just one digit. You'll go back to one digit or up to one digit. That being said, let's do this problem again. Think about now, where am I going to go with the decimal point? I'm going to start at the decimal point, wherever it is, and go towards the number I want to put into scientific notation. 1, 2, 3, 4. 2.57 times 10 to the negative 4. Number 41, add the polynomials. Adding polynomials or subtracting polynomials is about combining like terms. It's different than multiplying and dividing. When you add polynomials, and polynomials are these things. It could have one term, it could be 2, that's a polynomial, because it could have x to the 0 power, right? X to the 0 power equals 1, 2 times 1 equals 2. So, by definition. Let's just get rid of that. Alright, so you can have one number, a single one. For instance, a single one like -5, that's a monomial. If you have two of them, it's a binomial. 3 of them, it's a trinomial. But after trinomial, they're just all called polynomials. And then they're all just called polynomials. So to solve this, you're going to add like terms. So you have to figure out what is a like term. Remember what a like term is. The 3x squared and the 4x squared are like terms. The -5 and the negative 5x and the -5x are like terms. The 7 and the -5, those are like terms. You can only add like terms. Now watch what happens. 3, we have, we can put these together because we have that rule. Remember, these we should look at all these as signed numbers, and if they're all signed numbers added together, we can move them around. So you can, if you want to, move the ones that are like terms next to each other. So I have 3x squared plus 4x squared, and then I could add that, and I'll put a little parenthesis around this because these are negative. -5x, just to keep the signs separate. Plus, or I guess, forget the plus. Minus 5x, and then that's plus 7 minus 5. Okay, so I've separate them all out and put the same kind together, and now we just add them together. 3x squared plus 4x squared is 7x squared. Notice, these are x squares. I haven't added those together because we're adding these numbers. This is a thing, one type of thing. We could call it an x squared, right? We have 3 of them and we have 4 of them. If we add 3 of them together with 4, we have 7x squares, right? Doesn't change the exponent. Okay, same with here. We have a negative 5x and another negative 5x. That gives us a total of a negative 10x. And of course here, 7 minus 5 is 2. So our answer is 7x squared minus 10x plus 2. So when you're adding or subtracting, do not mess around with the exponents. You can't figure out what x squared is and what x squared is, or what x, plain old x is from this. They don't change if you're not multiplying them times each other. Remember, the definition of an exponent is it means that number is multiplied times itself, that number of times. And when you're adding them, you don't mess with those exponents. Number 42. Subtract the polynomials. Okay, so we have 2 more polynomials. We're going to deal with the combining like terms. But before we do that, this is subtraction. And it's much better, instead of taking each term, for instance, instead of saying, okay, I'm going to subtract 7x to the 6 from the like term negative 11x to the 6. You could try to do that in your head and then do it with this one and do it with this one. You're going to get mixed up. Don't do it that way. Instead, what we're going to do is whatever we're subtracting, we're going to negate it or multiply it through by a negative 1. We're going to make it its opposite. The reason we do that is just like if we were going to subtract, say we have 3 minus 5. Okay, so we've gotten in the habit of seeing this as a positive 3 and this as a negative 5, right? And just combining them, right? Or you could say, all right, well this means 3 minus 5. Okay, I'm going to change that to an addition. I'm going to make it 3 plus a negative 5. And I'm going to get the same number. I'm going to get negative 2. That's going to be the answer to that. So I'm going to do the same thing with these. I have 9x to the 7th power minus 11x to the 6th power minus 13. And this is minus 7x to the 6th power plus 2x to the 7th minus 6. Okay, so I'm going to change this to a plus, and I'm going to make these all the opposite signs. So this positive 1 here, make it negative. This negative, I'm going to make it positive. Okay, so now that I've changed these, I've made them opposite, right? I've made them opposite. Now I can just add them together, just like we did with 3 minus 5. I'll make this positive 5 the opposite. I'll add it together, but I'll make this the opposite of it, and then I can add them together. It gives me negative 2. I did the same thing down here. Okay, so now I can combine like terms, and you can put them together. There are a couple different ways to do this. You can put them together like I did in the last problem. You can just do it in your head and say, okay, 9x to the 7th plus a negative 7x to the 6th is, oh, nope, I can't add those two. Do you see that? I almost added those two together. But they are different. They are not like terms. And I don't know what they are. I don't know what the relationship is between them. I know that 1 has one more x multiplying times it, but I don't know how big the number is. It could be a 1, it could be a billion, right? So can't combine those two. I have to combine that with this one. Okay, so I could say to myself, okay, a negative 11x to the 6 plus a negative 7x to the 6, it gives me a negative 18x to the 6th. Then I have this 9x to the 7th combining with a negative 2, that's an x. Fat x. Okay, 9x to the 7th combined with the negative 2x to the 7th gives me 7x to the 7th. Okay, then the last two is this 13 and the 6, and that gives me a negative 7. Okay, but there's another way we could do this. Well, there's two other ways. One way is the one I showed you in the previous problem, and there's a way of stacking them up. Okay, so you put the like terms on top of each other and then just add them up, just like we've been doing since we were in first grade. Okay, so let's do that. We'll put them in order. So 9x to the 7th, in this is descending order, by the way, minus 11, or plus a negative 11x to the 6th, plus a negative 13, adding to that a negative 2x to the 7th. So you have to be careful to put the right ones under the right ones. Negative 7x to the 6th, positive 6. Okay, so when we add them together, this is a negative 7. This one's a negative 18x to the 6th. And this one is positive 7x to the 7th. See, so there's always a few different ways of doing a problem. You work a few of these and see what works best for you, and check and make sure you don't mix up the exponents. You don't mix up the x terms with different exponents. You have to combine like terms. That's actually the only hard part about this, is make sure you keep it straight. You could even cross out the ones you've already added together just to make sure you don't add them twice or add the wrong ones. Or for instance, one thing you could do is you could circle one type and then put a box around the other type, right? Depending on how many types you have. So I'm putting a box around the ones to the 6th power. I put a circle around the ones to the 7th power. And if I had another one, I could put like a triangle around. I mean, we're not going to be getting these two confused because they don't have a variable on them. But you find a strategy that works for you just so you can keep it straight. A lot of this math, the difficulty here is just keeping things straight so you don't drop signs, you don't add or subtract wrong, or some little thing that causes the whole problem to go haywire. And if you notice that a problem is getting harder and harder, maybe you've made a little mistake, because it shouldn't get harder. Usually, real life problems often do that. They'll get really thick and complicated, but the problems we work shouldn't get that bad. So you might want to go back and check your math just to make sure you didn't drop a sign or forget about a number. All right, enough said. Okay, multiply. This is multiplying a monomial times a trinomial. I don't even think you need to remember what that is, but trinomial. Notice the trinomial has 3. 1, 2, 3. And then the monomial 1, mono. Right? So we have a negative 10x to the 6th power times all this stuff in the parentheses. Negative 6x to the 6th, positive 12x to the 5th, and a negative 2. So this is really just a distribution problem. Remember, I've said before that, let's say we have two parentheses, and we have, well, maybe you weren't here for that. If you were, say there's a whole bunch of numbers in this one, and there's a whole bunch of numbers in this one. I'm just using these squigglies for numbers. We need to take each one of these numbers. Let's start with this one, actually. Each one of these numbers in this one and multiply them times each one in this one. So the first number multiplies times each one of these, the second one multiplies each time of these, the third one times each of these, and then you add up the remains. Add up what you've got when you're all done. And that gives you your answer. In this case, we just have one number multiplying times these three. So we have distribution. We're going to distribute this over this one, and this one. And then pay attention. We've got exponents. Now we're multiplying times exponents. So we're going to be changing the exponents, right? Okay, so you can spread this whole thing out. And you can, and what I'd recommend, if this is kind of confusing for you, don't do the thing in your head. Instead, write what this means. It means a negative 10 x to the sixth times a negative 6 x to the sixth plus a negative 10 x to the sixth times 12 x to the fifth. I'm going to run out of room again. And that's also plus, I'll write it here, negative 10x to the sixth times a negative 2. So that's what this is here. This one times this one, this one times this one, this one times this one, right? Okay, you have three multiplications here. Okay, so you just do all those three multiplications and you add them together. Now we're just multiplying exponents, really. So we have negative 10x to the sixth times a negative 6x to the sixth. We multiply the numbers times the numbers, right? And the variables times the variables. And we can do that because of the distributive property, the commutative property, the associative property allows us to do that. So negative 10 times a negative 6 is what? 60. And then x to the 6 times, it's a positive 60. Negative 10 times a negative 6 is positive 60. So then x to the 6 times x to the 6. Well, right, x to the 6 is 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. And just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or you can remember that if you're multiplying x to the 6 times x to the 6, you're going to have 12 of them. X to the 12th. Okay, so there we have the first one. Now we'll do the second one. And that's going to be, the outcome is going to be negative because we have a negative 10 times a positive 12. So that, negative 10 times a positive 12 is a negative 120. Okay, so now we have x to the 6th times x to the 5th, right? So now we have, instead of 6 of them, we have 6, but it's times 5, times x to the 5th. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's to the 11th power, x to the 11th. All right, and so now the last one is negative 10 x to the 6 times negative 2. So we multiply the numbers times the numbers. Negative 10 times negative 2 is a positive 20. And then we just add the x to the 6th. And there's no x we're multiplying that by, so we'll just keep the x to the 6th. And there's our answer. 60x to the 12th minus 120x to the 11th plus 20x to the 6th. And so here we did change the exponents because we're multiplying the x's times other x's. We're getting more of them. Just by the definition of what an exponent means, we've gone here from having 6 here times this 6 makes 6 times 6 x's times 6 x's makes 12 x's. So you can just add them up if you want to do it in your head, or you can just write them all. And I highly recommend expanding them all out so you see them all, so you don't make a mistake, unless you're really sure of it. Okay, number 44, multiply 5z negative 8 times 2z negative 5, or minus 5. Okay, so now here we have we have a binomial times a binomial. And this is where, if you're used to doing the FOIL method, go ahead and use the FOIL. But if you're not used to doing that, don't try to memorize FOIL. Because it doesn't help you when there's numbers any bigger than binomials, right? So, like I was saying previously in the previous problem, whatever's in the first parentheses, you multiply that times whatever is in the second parentheses. Each one, you multiply each one. We're going to multiply 5z times 2z, 5z times the negative 5. We're going to multiply the negative 8 times the 2z, and we're going to multiply the negative 8 times the negative 5, and then we're going to add them all together. Now you can do this in your head if you want. If you're used to doing this, so 5z times 2z would give us, I'm going to write it way down here, 10z second power, because there's two z's, right? Okay, now we're going to go, that was the first one. Now we'll do the second one, 5z times the negative 5. That gives us a positive times a negative is a negative, negative 25. There's no z we're multiplying times, we still just have that one z. Okay, now we're going to go to our 8, negative 8. Negative 8 times 2z. That gives us a negative 16z. Okay, now our negative 8 times a negative 5. Negative times a negative is positive. Positive 40. But now look, are we done? No, because we have two like terms that we need to combine. So when you're multiplying two binomials or more than, if there's more than one in the first parentheses, or the first number you're multiplying by the second one, you're going to have often like terms to combine. So don't ignore that. So negative 25 plus a negative 16. That gives us a negative 41z plus the 10z squared and the 40. So that's our answer. But like we did before, we can make little products out of this whole thing. We can make 4 products. Okay, so we'll start with the 5z. 5z times 2z. We have 5z times 2z plus 5z times a negative 5. 5z times a negative 5. Okay, and then we have negative 8 times 2z, so that's plus negative 8 times 2z. And then we have a negative 8 times a negative 5. So plus negative 8, I don't know if I can get it in there. I can't. Alright, it's going to have to go here. Okay, negative 8 times a negative 5. Okay, so we'll work each one of these out. Okay, 5z times 2z, 10z. 5z times a negative 5, negative 25z. Oh, this is z squared. See, look, I missed it. There's 2 z's there. Okay, negative 8 times 2z, negative 16z. Negative 8 times negative 5, 40. And then we're going to combine our like terms. And so we're going to end up with 10z squared minus 41z plus 40. Number 45. Now here you can notice we have a binomial times a trinomial. Again, the same thing holds. We're going to distribute the x over all 3 of these, and the negative 7 over all 3. Okay, don't feel funny about making products out of the whole thing. So the products we would get out of this, we have x times x squared, right? X times x squared plus x times 7x, x times 7x plus x times a negative 4, x times a negative 4. And that's plus, then we're going to do the 7, negative 7 times x squared. So plus a negative 7 times x squared plus negative 7 times 7x. So negative 7 times 7x plus negative 7 times negative 4. Negative 7, negative 4. Okay, and then we have to solve each of these products. Okay, so x times x squared was x to the third power. So there's a bunch of little exponent problems here. X times 7x, 7x squared. X times a negative 4, negative 4x. Negative 7 times x squared, negative 7x squared. Negative 7 times 7x is negative 49x. And negative 7 times a negative 4 is positive 28. Oh, I got it all in the same line. Okay, so now, we're not done though, right? Because we have terms to combine. So let's use the circle box method. We've got 7x squared here. We have a negative 7x squared here. We have, we use a box for this one, negative 4x here. We have a negative 49x here. Okay, so those are the only like terms. So I'm going to combine them. Now you can put them next to each other, because remember we're going to look at all these as signed terms and that are added together, so we can move them around if we want. You shouldn't feel funny about doing these extra steps. If you get a good grade because you do these extra steps, it's worth it. Alright? If you don't have to, don't do it. Okay, so we have x cubed, okay, 7x squared plus a negative 7x squared. That goes away. I'm just going to cross that out because they're opposites, they become 0. Okay, so negative 4x plus a negative 49x gives me a negative 53x. Negative 53x. And then we have our 28. And that's the answer. Okay, here we have, in parentheses, 2a minus 7, and that is squared. Okay, so now this is a special product, and if you know the forms these special products go into, well, you can do this very easily. But I highly recommend against it. We didn't spend a lot of time on it, and it'd be much better to do it the other way. So the other way, I mean the way we've been doing these, right? So 2a to the minus 7, it's 2a minus 7, in parentheses, to the second power. That 2 is actually a little bit big. That should probably be a tad smaller. Alright, that's better. Okay, so the way we've been doing these, this 2a minus 7 to the second power means there's 2 of them. We've got 2a minus 7 times 2a minus 7. Okay, distribute this over this over this one over this one over this one. Then you combine like terms. So we've got 2a times 2a plus 2a times negative 7 plus negative 7 times 2a plus negative 7 times, ran out of room again. Negative 7 times a negative 7. Okay, and we'll do the products of each of these individually. 2 times 2 is 4, a times a is a to the second power, or a squared. 2a times a negative 7 is a negative 14a. Negative 7 times 2a is a negative 14a. Negative 7 times negative 7 is a positive 49. Then we combine our like terms, which is negative 14a plus a negative 14a. So our total is 4a the second power minus 28a plus 49. That wasn't so hard now, was it? Of course, there's another way to do this, and I'll show it to you, but I don't think you should try to remember this, because unless you've done this a lot in the past, you'll get this mixed up. Because this is the square of the first one, the square of the second one, and 2 times the product of the two. So you probably noticed this when you did it. And you'd have to do a lot of these. See, so the square of the first one, the square of the second one is 49, and then 2 times 2a times a negative 7 is a negative 28a. But, you know, don't do it that way. I don't want you doing it that way if you're going to get it wrong, which chances are, if you're not real used to doing it, you will. It certainly does not equal 2a squared minus 7 squared. It definitely doesn't equal that. What I've noticed always happening every year with these special products is the students only partially remember them, so they only partially put down the right answer. So of course you don't have a partial right answer, you're going to get the thing wrong. So you can't go wrong by doing that distributive method. It'll come out right every time. Okay, here's another special product. And when you get into 137, you're going to be doing so many of these special products that you'll remember them. But for now, and even when you're in 137, you can always distribute it. So let's just distribute it, right? We're going to go 7p times both of those, and then we're going to go 3 times both of those. Okay, so 7p times 7p is 49p squared. 7p times a negative 3 is a negative 21p. 3 times 7p is a positive 21p. 3 times a negative 3 is a negative 9. Then we combine like terms, 49p squared. These two are opposites, so they disappear, they become 0, minus 9. So you can see that the special product here is the difference of two squares. And the difference of two squares is that. But I don't know, I don't think it's, at this point, it's worth the time to memorize them. Later on, if you do lots of these problems, you start recognizing it right away, to save yourself some time, but not that much time. It didn't take that long to do this problem. Okay, we've come to our last problem, thank God. And it's a division problem. We're dividing a binomial by a monomial. We're dividing, so again, we're using our exponents. Our exponents are what we've learned about working with exponents. We've been actually working with division of polynomials long before this. You may not remember, but if we had a problem like 3y equals 6x minus 12, for instance. Say we had something like that. When we were solving an equation, we had to get y alone. So we're going to divide this by 3, and we're going to divide this whole side by 3, right? So this cancels out. This is, we divide the 3 into the 6x and into the negative 12. You know, we can't do it just to one because we're dividing it into the whole side. And it's the same thing we're going to do up here. We can't just divide it into 1. The bottom term doesn't disappear by just dividing it into 1. You've got to divide it into both of them. So in this problem here, 3 into 6x is 2x, and 3 into negative 12 is a negative 4. Okay, we divided it into both of them. So we've been doing these for quite a while. Sometimes you get a fraction, right? 3, so let's say this wasn't 6x. Let's say it was 1. Okay, so then instead of 2, 3 into 1 is just a fraction, 1/3. Or, yeah, just a fraction, 1/3. So we would put 1/3 there, right? Let's say that this was not... let's just leave that. Let's move on to our actual problem. So we have 9r. 9r is going to divide into this number and this number. So just like in the it's just like distribution, only you're dividing into both numbers instead of multiplying times both numbers. Okay, so we can write this up separately. We can say, okay, this is 27r to the 8th divided by 9r plus a negative 45r to the 3rd power divided by 9r. Okay, so now it just becomes two exponent problems, and then the answers, we're going to add the answers together. Okay, so 9 into 27 is 3. R into R times itself 8 times. Well, think about it. We've got 1, 2, 3, 4, 5, 6, 7, 8 divided by one of them, right? Right? 1, 2, 3, 4, 5, 6, 7, 8, and there's 1. Well, we can cross cancel. We can cancel out one of them. So, because R into R is 1. So, the answer would be how many? 7r. R to the 7th. Okay, so that one's done. Okay, so this is plus 9 into negative 45 r to the 3rd. Okay, so 9 into negative 45, that's a negative 5. Okay, r into 3, r to the 3rd is r times r times r. So we could cancel out one of those, so we're going to have r to the 2nd. So there's our answer, 3r to the 7th plus a negative 5r to the 2nd, and we don't even need this plus sign. We just leave it just like that. Alright, let's do one more and call it a day. This one's harder. You're not going to get one this hard. But let's do it. This one makes a lot of sense to make them 3 separate divisions. Remember, we're going to divide the 6x squared into each one of these. So try to do it. Actually, well, I should have said this before, so I'm not going to even say it. But try to do this before you watch me do it. See if you get it right, okay? Okay, so here it goes. We're going to make this, okay, 6x to the 5th is divided by 6x squared, and that's plus a negative 2x to the 3rd divided by 6x to the 2nd power. And then we have, that's plus 12 divided by 6x 2nd power. Okay, so we can do them one at a time. Okay, these 6's are going to cancel out. Here we have 5 x's and 2 x's. Now if you need to do this on a piece of scrap paper, right? We've got 5 of them and 2 of them. 1, 2, 3, 4, 5. We've got 2 down here. So these 2 cancel 2 of those up there out. We have 3 left. So what we have is x to the 3rd power. That's it. Okay, plus whatever this is. Okay, so we're going to have here 6 into negative 2. Well, that's a negative 2/6. So we have a fraction there. X to the 2nd power into x to the 3rd power. There's 3 up here, 2 there, so we only have 1 left. We're going to have x to the 1st power, just x. Notice when you're dividing exponents, and they have to have the same base, by the way. I don't think I ever mentioned that in this program here. But they have to have the same base, or you can't subtract the exponents or do anything to combine. Just if you have x and y, if you have x to the 2nd power over y, you're going to have x to the 2nd power divided by y. You can't do anything with it, right? Only if there was a y up here too, then you could cancel. You could cross cancel that y. See, something like that. Anyway, let's not worry about that right now. Okay, so now we have 6. The 6 divides into 12, but the x squared doesn't. There's nothing on top to divide. I mean, the only other thing you could do is you could put this on top and make it a negative, x to the negative 2 power, which we don't want. We don't want, because that would give us a negative exponent in the answer. We never want that. So we'll have 2, whoops, let me not make it so big. This becomes 6 into 12 is 2. That's over x squared. That's our answer. And this one here, well, we have to reduce that, right? It becomes a negative 1/3. So, of course, I've used up all the room again. Let's just stick their final result over here, kind of sideways. So we've got x to the third power minus 1/3 x plus 2 over x squared. Oh, what a mess. All right, where can I put that? I'm going to put it way on top. Okay, so we have x to the third power minus 1/3 x plus 2 over x squared. Okay, so try that yourself and see if you can get this answer. All right, good job. And okay, we made it to the end. So the test is not hard. The final is not hard. If you understand how to do these problems, not only just understand it, but have some practice doing these kind of problems, and can get them right, you'll get an A on the final. The final is half multiple choice. The problems are easier than the ones we just did, and you just have to understand the basic concepts, and then you can attack these things and take them apart and figure them out yourself. A lot of you did quite well on the exponents in the previous test. And those of you who didn't, get some practice with them. And you can figure it out. It's not that complicated. The worst part is our mental attitudes towards what we think is just too hard. So think of this test as a challenge. You've met other challenges in your life. Look at it as a challenge that you're going to do well with. Take it on as a challenge and with some enthusiasm for, hey, I can do this. All right, enough said.